Okay, applications of integration. They're the worded problems. They're the bum ones. They're the ones that get us the marks, though. So we're going to look at three applications of integration. We're going to look at the average value of a function. So this is kind of maybe a formula we haven't seen before, but it's nothing that we don't know. And these questions come up relatively regularly, and you often don't spot. Kids often don't spot what the question is asking. So keep this in your brain. So what it's saying is it's basically working out an average. It's working out like this. We pretend that we've got a rectangle. So if you think the area under the curve, which includes that bit, but not that bit, and does include that bit, can be averaged to the shape of a rectangle. We're also going to look at the motion in the straight line, and we're also going to look at rates of change. So average value of a function, the first one. Find the average value of the function f of x equals x squared between 0 and 2. Illustrate with a horizontal line. Okay, so we'll see what that means. So from that previous formula, it's basically a half. 1 over, that's going to be a half of the actual integral. So add a power divided by a power, we end up with 4/3. So there's the graph y equals x squared. There's the point 2. There's the point 0, because it's x squared. If x is 2, x squared is 4. So basically what they're saying is the area of this rectangle is the same as the area from 2 to 0. So it's the same as the area under the curve. So if we think about it, we know the height's 4 over 3 because we just worked that out. And we know that that distance there is 2 because that's the x coordinate, the x coordinate is 2. So if we work out the area of that rectangle, the area of the rectangle is 4/3 times 2, which is 8/3. And if on our calculator, if we integrate x squared from 2 to 0, we get 8/3. We probably work that out anyway because we've got the 8/3 there and we just found a half of it there. So this is obviously a simple example, but it kind of explains what's going on. And don't forget, illustrate with a horizontal line. There's a horizontal line that we need to put in. Motion in a straight line. So given a rule for acceleration, and we can use anti-differentiation and some additional information, we can usually find the velocity and the position. So don't forget, if we differentiate distance, we get velocity. If we differentiate velocity, we get acceleration. And we can go back the other way. So what's happening here? We've got the velocity and we want to find the distance. So we're going to have to integrate. So integrate this, add a power divided by a power, add a power divided by a power plus c. And this is what this additional information they say here means we can find c. So we're told that when t equals 0, x equals 0, so c equals 0. So it's positioned in terms of t. A is t squared minus 4t. B, find its position after 3 seconds. So when t equals 3, x equals minus 3. T squared is 9. 4 times 3 is 12. 9 minus 12 is minus 3. So x is minus 3, or the body is 3 meters to the left. 3 meters to the left of O. Average velocity, so it goes from minus 3 to 0 in 3 seconds. So it's minus 1 meter per second. D, find the distance traveled in the first 3 seconds. So the first 3 seconds, we're going to find what it was at the start, yeah? So to find when the body is at rest, if it's at rest, it means it's not moving, so the velocity is 0. So if the velocity is 0, we get t equal to 2. So when t equals 2, sub in, we get x equals minus 4. So the body goes from 0 to minus 4 in the first 2 seconds, and then back to minus 3 in the next second. And sometimes I like to draw a little picture here because it helps me. So initially, it goes from 0 to minus 4. So it's moved 4 units. We're talking about units. What we talking about? Meters per second. Then it goes from minus 4 back to 3. So that's another 1. So altogether, is travelled 5 meters in the first 3 seconds. So the average speed, 5/3 meters per second. This helps me. Maybe it'll help you. Rates of change. So the rate of change, here's an example with temperature and time. So they're using the capital T for temperature and the lowercase t for time. Time's in minutes, temperature is in degrees centigrade. Let's get the graph of dt by dt. When you say it. So we're sketching this graph here for t greater than 30. So because that's in brackets, we know that it means that we take the opposite sign of that. So it starts at 30. It's a negative gradient, so it goes this way. So it's got a negative gradient of half. Negative gradient of half. So because we've not put any scale on there, we're fine. Let's get to the other one. So before we look at that, let's look at this. dt over dt is 1 over dt over dt. I love saying this because it makes no sense. So it's 1 over that. And of course that 0.5 is a half, so we can write it that way. Flip it up the other way, so it ends up being -2 over t minus 30. So just sketching that. And again, t is greater than 30. So that's what that one looks like. Use our CAS for that. We can even type that into our calculator, and it gives us -2 over t minus 30. So we can even do it that way. Find the area of the equation enclosed by the graph, the x-axis, and the lines t equals 35 and t equals 120. So that's telling us it's going from 120 to 35. We're just doing this straight on our CAS. We know that because it's below the line, it's going to give us a negative answer. So if we put a negative there, it's going to give us a positive answer. Or we can just type it into our calculator and realize that we've got to give the answer as a positive because it says find the area. 2 decimal places. What does this area represent? So this is going to be a bit where you're going to forget, and you're gonna sort of miss out on this, and it's often going to be worth a few marks. So it represents the time taken for the liquid to cool from 120 to 35 degrees C. And that's minutes, isn't it? Yeah, so that makes sense, doesn't it? If you've got something 120 degrees and it cools down, it's take about 5 minutes. I can imagine that would be the correct answer. So 11K is just a bit of a summary. So you can use this together with the chapter summary to prepare for the test on Friday. So are all your exercises completed? Tick. Chapter 11 review done? Tick. All the exam questions done here? Tick. Skill sheets done? Tick. Notes up to date? Tick. Done all those things, you can go and play. So quite a bit of work there to do. We've got ages to do it because the test is not until Friday. Over and out.